and the launch team was ready to go. This is Atlas Mission Control live from Cape Canaveral, making final preparations for liftoff.
Atlas Systems propulsion, go. Hydraulics, go. Pneumatics, go. LO2, go. Vehicle electrical, go. Light termination system, go. Melon utilization, go. Centaur Systems propulsion.
At Cape Canaveral, some long-cherished assumptions about US space technology could very soon be rewritten. For the first time ever, an American rocket is scheduled to blast into space, powered by a Russian rocket engine.
Go. Vehicle electrical, go. Light control, go. CCLS monitor, go. Light termination system, go. Telemetry, go. RF, go. Complex systems instrumentation.
We thought maybe we misunderstood each other. The performance of the engines were probably 10 to 15% higher than what we had in the United States.
Booms, go. Launcher, go. Water, go. Complex electrical, go. Allen monitor vehicle loads, go.
It wasn't the same technology we're used to. It was a paradigm shift in what we were expecting.
LO2, ready. LH2, ready. Vehicle electrical, ready. Light control, ready. Atlas Systems propulsion, ready. Hydraulics, ready. LO2, ready. Vehicle electrical, ready.
This is Atlas Mission Control at T-minus 5, 4, 3, 2.
Behind the doors of this warehouse in a distant part of Russia lie what for 20 years was a closely guarded secret. A cache of rocket engines designed for the most ambitious space project ever to be undertaken by the Soviet Union. Today regarded as some of the finest in the world, the engines use a unique technology developed by Russia at the height of the space race. A technology so ambitious that Western rocket scientists thought it impossible to master.
The Russians were very secretive at that time, and although they said they were doing something, they did not tell us what they were doing, and in fact it took a great deal of intelligence gathering to really understand what their direction was. The really important things were having good, clear pictures of what they were building.
In the 1960s, the spy satellites of the CIA were keeping regular watch on the Soviets' vast space launch complex, the Baikonur Cosmodrome in Kazakhstan.
In March, April '63, we saw at least some initial what would be called stakes in the grounds for surveyors and stuff like that in the area that was undeveloped on the Baikonur Cosmodrome. The size of the assembly building, the causeway had all the earmarks for a very large launch vehicle indeed. It was like, hello, what's going on here?
The satellite images clearly showed the construction of a new causeway leading up to two huge launch pads side by side. To the CIA analysts back in Washington, the launch pads were the first hard evidence that preparations were underway for the assembly of a huge new rocket. The sheer size of the complex could mean one thing only. The United States was now in a race to the moon.
In the beginning of the 60s, the Russians were far ahead of us. They had better rocket engines, so with that rocket power, they were able to do lots of things that we were simply unable to do. It was a wonderful period for them. First ICBM in August of '57, Sputnik 1 in October of 1957, and then first man in space, first woman in space, first 3 men in space, first extravehicular activity, first spacecraft to hit the moon.
Russia's achievements in space were down to a unique approach to rocket design, pioneered by one central figure. The anonymous chief designer, Sergei Pavlovich Korolyov, head of OKB-1, Experimental Design Bureau No. 1, and Russia's most senior rocket scientist.
He was very much the dominant figure in the Russian space program. There's simply no counterpart, for example, in the US program. He had responsibility not only for the beginning years, the Sputniks, the manned program, communication satellites, spy satellites, planetary spacecraft. There's no American who had that kind of responsibility. You'd have to equate his work with 15 aerospace companies and about 4 or 5 NASA centers. Very, very much the dominant figure.
His identity a state secret. As chief designer, Korolyov was the most powerful figure in the elite core of the Soviet Space Design Bureau, reporting directly to the Kremlin. Korolyov was the key figure behind Russia's unique approach to rocket design, a pragmatic, hardware-based philosophy in which important design questions were only resolved after full test flights.
In a lot of respects, they were well ahead of the game, but the reason they were well ahead of the game is because they had actually put all the hardware together and had applied that technology far better than we had.
The conquest of space a political priority, Russia's breakthroughs had come through a hands-on approach in which rockets had been built, flown, and improved. And if there were explosions on the way, that was something to be learnt from. From his headquarters at OKB-1 in the suburbs of Moscow, Korolyov started work on a manned lunar mission, with that same experimental, hardware-based design philosophy. But the sheer challenge of getting a man on the moon was a problem on an altogether different scale from anything they had previously undertaken. With the United States already enjoying a head start from their declared goal of landing a man on the moon by the end of the 1960s, the odds against Russia winning were beginning to stack up.
Expediция на Луну. Одного космонавта.
As Korolyov's deputy, Vasily Mishin had started working on rockets at OKB-1 after World War II. From the Earth's gravity and the Moon's distance, they soon worked out a lunar mission would need a huge new rocket.
In order not just to get to the moon, but to land on the moon and to bring back an expedition consisting of at least one person, for that you need to put 100 tons into the Earth's orbit. And that means you need to have a rocket which has a starting weight in the region of 2,000 tons.
To build a rocket of the size needed, and within the Kremlin's deadline of beating the Americans, was a challenge beyond any the chief designer had previously undertaken. Korolyov quickly realized they would need new, vastly more powerful engines for the huge new rocket. But Korolyov did not see eye to eye with his usual manufacturer on the kind of engines the new rocket would need. He had no choice but to find an alternative supplier.
Korolyov was forced to go to an aircraft designer named Kuznetsov in Samara. This is a fellow who had designed very good aircraft engines, but that was all the experience he had. That was a big risk for Korolyov.
Kuznetsov had built up a formidable reputation as a jet engineer, having designed the engines for the first Soviet long-range strategic bomber. But he had never worked with rocket engines.
Kuznetsov did not have any experience in building liquid propellant engines, but when he looked at their configuration, he saw that liquid propellant engines, rocket engines, did not pose any more problems than aircraft engines, and realized that this challenge could be solved.
Valentin Anisimov had worked under Kuznetsov on jet engine design, but when the chance came in 1962 to apply his skills to rocket engineering, he seized it. From the Kuznetsov Design Bureau in Samara, on the banks of the Volga River, 1,000 kilometers from Moscow, the team began working out what kind of engines the colossal new moon rocket would need. The basic design of rocket engines is simple. Oxygen and fuel are pumped separately at very high pressures into the beating heart of the engine, the combustion chamber, where they are ignited, propelling the rocket forwards. The higher the combustion chamber pressure, the higher the performance of the engine. Those very high pressures are built up by pumps, driven by a gas turbine fired from the preburner, a mini combustion chamber that draws off part of the oxygen and fuel supply. Faced with the deadline of beating the United States, it became obvious to Korolyov there wouldn't be the time to develop the kind of gargantuan engines needed for the new rocket, christened the N1. With Russia lacking the kind of industrial infrastructure of the Americans, there would only be time to make small but highly efficient engines for the N1 rocket, a total of 30 for the rocket's first stage.
In order to lift off, you have to have more thrust than the gravitational force holding you down. And in our case, we decided to go with 5 engines to do that, provide that thrust. And in the case of the Russians, they used 30 engines. So they used engines that were about 1/6 the thrust level of our Saturn V engines. You know, it's a matter of engineering choice which way you went.
But the choice to have 30 engines was one that was forced on Korolyov by Russia's lack of resources. With so many engines, the chances of any one failing would massively increase. To overcome those huge odds and achieve the efficiency and performance Korolyov demanded, the engine designers would have to crack a problem that had always been shied away from as too difficult and too dangerous. At that time, all American and Russian rocket engines worked using an open cycle, in which the exhaust products from the pre-burner that drives the pumps are dumped over the side. A simple but wasteful design. But for the high-performance engines Korolyov demanded, that inefficiency was unacceptable. Russia's engine designers would have no choice but to take an untried and highly risky step. They would have to close the cycle and find a way of safely channeling the exhaust products from the pre-burner back into the combustion chamber to be refired. A potentially explosive process, but one that can boost the lifting power of the rocket by 25%.
Closed-cycle engines require a much better understanding of the combustion process and a much better control of all of the stages in that combustion process. As a consequence, you can blow up a lot of engines trying to build one that works. And I think that the Russians did blow up quite a lot of engines.
Mastering the new closed-cycle technology with their experimental test-based approach would take time. Time the Russians lacked in their race to beat America to the moon. Not everything went badly. The Bureau's experience with jet engines gave it a lateral and innovative approach to rocket engine development. The Kuznetsov team realized there were strong similarities between the turbopump assemblies in jet engines and rocket motors.
In the construction of both airplane engines and rocket engines, there is a battle to keep the weight down. In our design, the booster pumps are inside the main pumps. This dramatically reduces the external piping, improves reliability, and decreases weight.
The compactness of the engine was both original and highly elegant.
Well, this design was really a radical design for the early 1960s. Whenever you're designing engines, you want to make it as simple as you can with the minimum amount of parts. So the Russians have typically chosen the single shaft type design for the turbo machinery, which really simplifies and adds to its efficiency and performance.
By 1966, with the key technical challenges behind closing the cycle resolved, the highly efficient engine the chief designer had asked for was within sight. But the project was then struck a devastating blow. During routine surgery in January 1966, Korolyov died. The one figure with the authority and vision to galvanize the system behind the goal of beating the Americans had gone. As the N-1 rocket finally started to make its way out to the pad at the Cosmodrome, the odds stacking up against Russia in the race to the moon looked formidable. By 1967, the first N-1 moon rocket had been assembled at the Cosmodrome. Standing 35 stories high and weighing the same as 400 double-decker buses, Russia's answer to America's Saturn V presented an awesome sight.
I have to say that prior to every launch during those years, we felt a certain trepidation. We were still affected by the large number of accidents that we had witnessed with our own eyes, pretty much since 1947.
Vasily Mishin had been appointed to take over as chief designer in the wake of Korolyov's death, in charge of the 24-hour shifts, working to prepare the rocket for launch. Russia lacked the huge facilities needed to ground test all 30 N-1 engines as a whole. The first launch would take place with the rocket and its system of closed-cycle engines still untried. There would be no alternative but to finalize the design in the same way that all other Russian rockets had been perfected, through a series of full test flights.
Because of our limited resources and capacity, we had to do the bulk of the development of the rocket stages during test space flights. We planned 12 unmanned launches, and we only planned manned flights for the 13th and 14th launches.
The first unmanned test of the rocket took place in February 1969.
Well, when the rocket left the launch pad, in those first few moments there was a sort of uplifting feeling. Yes, it's taken off. Yes, it hasn't blown up on the spot. This was already a great victory. And then, what happened next has gone down in history. There was a fire in the rocket, followed by an explosion. And it has to be said that at the time, we felt this was bound to happen. We hadn't finished working on it.
A minute into the flight, the rocket exploded 40 kilometers from the launch site. Metallic debris had caught inside an engine.
Of course I felt bad. Do you think you would feel good if your engine blew up with a thrust of 4,500 tons? You feel very bad.
Controlling a rocket with 30 engines was proving very difficult. But with another 11 unmanned launches still to go before the first manned flight, the engine's control system was improved ahead of the next launch in July 1969.
This is the launch now, you see. It stopped. Now it's going to fall.
Seconds after takeoff, the rocket fell back onto the pad, exploding with the force of a small nuclear bomb.
We hadn't left the dugout 10 kilometers away when it crashed. That's what saved us. If we had come out, we would not have survived.
The rocket had been launched before the ambitious closed-cycle engines had been perfected. While the debris was still being scraped up from the floor of the Kazakh desert, the race to the moon had come to an end. Just 2 weeks after the N1 disaster, the Americans were celebrating victory in the wake of the successful Apollo 11 mission. But the Russians didn't give up there. True to their practice of evolving the design through actual launches, the engine and rocket were steadily being improved. To prevent the intake of debris, filters were fitted to the engines, and the launch pad was rebuilt ready for the next tests in 1971 and 72.
Well, this is the third launch. I've only seen this on film. I didn't actually see it in real life, only the traces. There's the fire.
And their problems didn't end there. The fourth rocket also blew up. The moon race may have been lost, but by the early 1970s, the proven Russian system of refining through test flights was delivering real improvements in the rocket. A new engine, designated the NK-33, was being finalized, in which the gremlins identified from the launch failures had been ironed out. With new filters and protection against vibration, the high-performing closed-cycle engines the designers had dreamed of were finally ready to fly.
Experience showed that Kuznetsov's engines could be made reliable, But for that, we needed those very 4 years by which we lagged behind the United States.
But at the very point the NK-33 engines would be able to prove their worth, the program was cancelled. The Politburo's patience with the N-1 had finally run out. In 1974, the political imperative behind the moon race had now gone. As a result, the entire N-1 program was cancelled on the orders of the Kremlin, and Mishin was sacked as chief designer.
What if I was unhappy? These things happen, of course. But there were a lot of reasons. I can't say that I was fine. Things were bad. But I survived. I'm still here.
At Baikonur today, the desert is slowly reclaiming the colossal works of the N-1 project. After the cancellation of the program, the Soviet leadership ordered the complete destruction of all the remaining N-1 rockets and their engines. The entire history of the program was suppressed, and the remaining M1 stripped down. At the Cosmodrome, parts of the rocket were even converted into pigsties.
What does a man feel when he was responsible for the creation of a project, for nurturing it, when this system was created and it worked, and suddenly, at the height of your involvement in the creative process, you're told to cut it short, to put a stop to it? There was a disappointment that is difficult to convey now.
The story of the N-1 remained a shameful secret until the early 1990s, when, with the fall of the Soviet Union, information started to trickle out. Visiting American rocket scientists, the first to delve into Russia's achievements in space, were starting to get details of an engine for sale. The engine used a kind of technology very different to what the Americans were familiar with.
The description to me was I think there's something there, go find out. So off we go to start developing contacts. You know, who do you talk to? How do you get there? You know, the barriers that we were looking at looked to be almost insurmountable at the time, but we chewed away at it, finally got the right connections and started seeing some of the data.
Information was emerging about an engine with unusually high performance specifications.
When we went to Moscow, the word got around that we were there, and we went, several times. And what happened is people started coming to our hotel. And one of the people that came was a gentleman from a test facility in Salda, up in Siberia, where they had tested the NK-33 engine. And through him, we were able to arrange a meeting with Mr. Kuznetsov himself.
An unprecedented invitation followed to visit the design bureau at its secret location in Samara. There was something they wanted the Aerojet visitors to see.
Literally a forest of engines. There were over 60 engines stored in this one area, just side by side. To see that kind of quantity of this tremendous asset was absolutely incredible.
Есть такое выражение.
He was speechless. There's that saying, it took his breath away. He saw them and his jaw dropped. There was a forest of engines. He was amazed.
In defiance of the Kremlin's orders, the stockpile of NK-33 engines left over from the moon effort had been preserved in a warehouse safe from prying eyes for almost 20 years.
Поэтому неразумно было работающие двигатели.
It was not sensible to consign engines that were designed to last and to work
Под бульдозер
to the scrapyard to be melted down.
он по своей инициативе.
On his own initiative, Kuznetsov collected together all the engines that had been made and preserved them.
И сохранил их.
When you build a rocket engine, it's just unbelievable the amount of hours that go into each one of the engines, and it's a dedication. It almost becomes like your child. There has to be a value somewhere. They had no idea where, so they just kept them.
Now worth millions of dollars, with the visit of Aerojet's engineers, it looked like Kuznetsov's foresight in preserving the engines might pay off. But with the NK-33 never having proven itself in flight, Aerojet had some tough questions to ask about the performance specifications being claimed for the engine's closed cycle.
Well, engineers never just say this is fantastic. We're a very a bit of skeptical type of people. We have to prove things to ourselves technically. We wanted to know for ourselves that we could back up the claims.
That skepticism was deepened by the fact that the closed-cycle technology behind the NK-33 was only poorly understood in the United States.
They were doing things at a level, they were operating at levels that some in the United States were saying as recently as 15 years ago, you can't do that. And yet they had been doing it for over 10 years. So they had really protected their technology, and those of us in the industry did not know how they were doing it.
The only way those doubts about the engine's reliability and performance could be resolved would be in a full test firing, the first in 20 years. An engine was sent from Samara to the test stand at Aerojet's facility in Sacramento, California, for a proving test set for October 1995.
Bring up the sequence computer and load sequence JSQ NK firing program. Monitor supply pressure. Verify close, locks, engine safety valve. Open engine GN2 start purge supply valve. Open engine start purge tank isolation valve. Verify close, locks, run line drain valve.
Трудно переоценить те волнения.
Well, it is hard to overstate the anxiety that we felt before the test. My hair had already gone white, and I thought, can it get any whiter with all that worry? There was worry, stress, every kind of stress. Nervous, physical, moral, psychological.
Notify when pressure reaches 3,000.
Pressure's up, pressure's 3,000.
Stand by for test. NKP2 Q01 1A001 on the countdown. Siren on. Off at the second bell. Press the camera iris. Countdown. 5, 4, 3, 2, 1. Fire.
PC's up. 1512, 77%, looking good. 14,000.
And you're wondering, oh, this is very, very powerful. Is it going to hold together? Is our test stand going to work?
Stand by for throttle up. 100% thrust. PC's looking good, 2100.
The test conductor is calling out certain critical things, and in your mind you're saying, yes, that's right, it's good, it's good.
The engine hit each of its specifications. Russia's alternative engineering approach had delivered a technology that, though 20 years old, America had still not managed to equal.
21 seconds. Shut down.
We tested it at 10 a.m. That was about midnight here. Everybody was waiting for us to call and let them know how the test had gone. And we said, it's okay. It worked.
Aerojet now had all the proof they needed to go out and sell the engines for use on the latest generation of satellite launchers. The man to have bought them knows a thing or two about the rival merits of Russian and American space technology. George Muller, the engineer once at the helm of America's race to the moon.
I first came across the NK-33 when we began the development of the K-1, our reusable launch vehicle. We were looking for high-performance engines, and we knew about the Russian engines in general, but it wasn't until then that we really began to understand how efficient they really were. The efficiency of these engines is very good, better than anything else available in the world today.
Start flight pressurization. Roger, going to flight pressures.
The NK-33's closed-cycle technology has now been taken to a further stage in a new Russian engine. That engine is about to make history by being the first to fly on an American rocket, a rocket that started life as an intercontinental ballistic missile pointed at Russia.
2 minutes, 15 seconds.
You know, for me, it's the same every time. It doesn't get any better or easier. This one is a little more tense because it's a maiden voyage, but yeah, it doesn't get any easier.
Rocket scientist John Karras of American space giant Lockheed Martin is on his way out to the launch pad at Cape Canaveral, just a few days ahead of the inaugural flight of the latest Atlas rocket, powered by a Russian RD-180 engine. Twice the size of the NK-33, the new RD-180 takes Russian closed-cycle technology to new limits of performance, offering thrust levels almost 5 times those of a jumbo jet. If the launch goes as planned, the RD-180 will enter the history books as the first Russian booster engine to power an American rocket and its communication satellite payload into orbit.
We're working a couple small items this morning, really one item. So we're doing final checks and we're closing things out. In about an hour from now, we'll be actually buttoned up for launch, and we really won't do anything the rest of today, Friday, Saturday, or Sunday, and we'll come in and power up on Monday and go for launch.
The RD-180 is a direct descendant of the huge closed-cycle engine built in the 70s for the abortive Russian space shuttle program. It's been tailor-made for Lockheed Martin by the MPO Energomash Design Bureau, today one of the leading manufacturers of rocket engines in the world. Though Energomash has successfully powered over 2,000 rockets with 11,000 engines, this will be the Design Bureau's first ever launch from Cape Canaveral.
And he always wants to make sure that he is taken care of when he arrives.
Where the old Atlas rocket used to be driven by 5 engines, the RD-180 is so powerful that the new Atlas III will use just 1 and still offer 10% higher performance.
In rocket science, it's not done to make forecasts about the launch. As the saying goes, you have to knock on wood.
For this remarkable marriage of Russian engine and American rocket to have even reached the launch pad is only the result of a long and sometimes difficult collaboration between these two Cold War rivals. Bob Ford was one of the first people to assess Energomash's technology in the early 1990s.
Our initial impressions was that we were being fed a line of something as a come-on, and we couldn't understand how they could be getting the type of parameters they were talking about. They were talking about chamber pressure inside the engine that were higher than anything that we had in the United States.
The chamber pressures being claimed for the engine were above those found in the American space shuttle and outclassed standard rocket motors by a factor of 4 to 1.
We thought maybe we misunderstood each other. We were being told things that we couldn't validate against our own experience, and we had to go off and check because it just didn't. It wasn't the same technology we were used to. It was a paradigm shift in what we were expecting.
5, 4, 3, 2, 1.
That gap between American expectations and Russian performance was explained by Russia's hardware-focused engineering tradition. Building on the technology first developed for the NK-33, the RD-180 uses a high-performance closed cycle that had been rejected as too risky by engineers in the United States.
All right, PC, we got a normal end-of-line cutoff.
The engine design itself was a departure from what the Americans would do for an engine design. All the oxygen inside the engine actually flows through the preburner, what actually drives the turbine.
The oxygen-rich closed cycle would mean far higher combustion chamber pressures, but it was not without risks. The hot oxygen gas coming from the preburner is so flammable that even the metal engine itself can catch fire and explode.
If you had an ignition source, you could, and we've seen it on some engines, actually just burn the engine up. The aftermath is something to see. It looks like you've seen large castings that probably are 3 inches thick, literally melt like candle wax.
From their factory on the outskirts of Moscow, Energomash have, since World War II, produced over 100 engine designs, each one an improvement on the last. By incremental development, they succeeded in mastering a combustion cycle that, because it was oxygen-rich, had been rejected as just too dangerous by rocket scientists in the United States.
It's not only the Americans who didn't manage to do that, but also the Europeans, the Japanese, and the Chinese. To do this, we had to approach how the fuel is burned in the preburner very carefully so that the temperature field is uniform, and to choose the right kind of materials and production techniques.
Energomash had found a way of using the closed cycle to take chamber pressures to new limits while protecting the inside of the motor from the greater risks of fire. A whole new class of high-temperature resistant stainless steels, unseen in the West, was invented to cope with a hazardous oxygen-rich environment. With that kind of technology, Lockheed Martin's skepticism evaporated.
It was very easy to persuade them. We said, here's the engine, here it is in the production unit, here it is at the test center, and now we're going to test it. Look at the data. What better way to present it than with a concrete test of a specific iron engine, to be persuaded that it works, and works reliably.
Lighthouse monitor, telemetry, channel 2.
Roger. Attention on complex 36A. There'll be loud venting on the east side of APAD ramp. I say again, loud
At Cape Canaveral, the ground controllers have started their final checks.
Clearance around the C-band and S-band antennas.
Today, The RD-180 engine offers performance and reliability beyond anything achieved in the United States, with its billions of dollars of investment in space technology. Exposure to Russian design philosophy has forced American technology giant Lockheed Martin to question some of its own most cherished working methods.
Clear back, except for the green team.
The Russians design engineers design the engine. They have all the drawings. They hand the drawings across to the manufacturing engineers that are on the floor that are actually going to build this thing, and those folks actually take over the design at that time. Whereas in the United States, the design engineer would design something, and he'll hand it across to the factory floor, and the factory floor will say, I got to meet this drawing. And what happens is cost of articles go up, scrap rate goes up, requirements for tighter and tighter machines go up, and we turn the factory into more of a technology lab.
Back at Kuznetsov, the team that designed and built the NK-33 is still together. Though now in his 70s, Valentin Anisimov remains chief designer of engines. He and the team are ready to resume production of the NK-33.
We've been waiting for this for a long time, for 20 years. All the decisions on that have already been taken. Production of these engines will be restored in Samara.
Highest winds we saw in the area were over 20, 23 knots, but nothing more than that at the Cape. So there's currently no lightning advisories for the Cape.
As the Atlas mission controllers take their places for the countdown, with the launch of this new rocket, Russian rocket engine technology will finally have come in from the cold.
Temperatures in the mid to upper 70s, and right now holding at 60% chance of no-go at the beginning of the window. However, improving conditions as we approach the second half of the window.
Energomesh's team will be able to monitor the engine's performance from their own control room for the duration of its 3-minute burn.
Spacecraft on internal power. Roger. Ready to report to resume countdown. Atlas systems propulsion. Go. Hydraulics. Go. Pneumatics. Go. LO2. Go. Vehicle electrical. Go. Light termination system. Go. Electrical. Go. Power monitor vehicle loads. Go. EV control. Go. Operation safety.
10 years after the end of the Cold War, old-fashioned, hands-on Russian engineering is about to teach American high technology an uncomfortable lesson.
This is Atlas Mission Control at T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, and the RD-180 engine roars to life and liftoff!
The idea that the technology in the United States was not equal or superior to the Russians was a very hard pill for a lot of people to swallow. It was very difficult to tell somebody in the government that all this money that they've put into it, really, there was still a technology edge over in Russia over what we had here.
And everything continues to look normal on the engine. Staying steady at 87% thrust. Engine parameters continue to look good.